Okay, um, question for you guys. What level of efficiency would you accept, let's say, from something that you use every day? How efficient would you accept? What's the lowest efficiency as a percentage you would accept for something that you use a lot? You would accept that it would run at 10% efficiency. Every day, you use it every single day, okay? And you're the one who's got to put the energy into it. Okay, it would be great if it was 100%, but I mean, we know that that's impossible. The laws of thermodynamics forbid it, right? Otherwise, it would be a perpetual motion machine, which would be great, but we can't do that. So what's a percentage that we could, like, honestly accept? That would be, let's say, good. 40%? Okay. I mean, we know that when we convert energy from one form to another, some is lost, right? There's always this friction, and there's, sound and heat and things like that that are all produced, okay? 40%, I mean, that seems kind of low, but it's not unreasonable. What if I told you that every day you accept 12%? Every day you accept 12%. Because I will bet every day you get in the car and go somewhere. Okay? Cars run depending on their size, or whether they're a car or a truck, and how many cylinders, how big the engine is. They run anywhere from 10% to 18% efficiency. If you had a hybrid vehicle, you might, if you drove it absolutely properly, be able to get it over 20% efficiency. Okay, now here's where that really hurts. If you put $100 worth of gas in that car, only $20 of it actually drives you forwards. The other $80 is wasted. And that's if you're in a reasonably efficient car, okay, at 20% efficiency. If you're running in, let's say a big, giant, heavy-duty diesel truck, okay, you're probably looking at more like $90 of that $100 is wasted. And 10% actually effectively drives you forward. A little depressing when you think about it, okay? But that's what we accept because of the way engines work. What's the initial source of energy for an internal combustion engine? Gas, which is what kind of energy? Chemical. Okay, it's chemical energy. Okay, and we're trying to convert that initial source, chemical energy, into what? Kinetic, which is a form of mechanical energy. We're trying to go from chemical energy to mechanical energy. Okay, that is one of the least efficient methods of producing chemical energy, of producing mechanical energy, because chemical energy is a form of potential energy. In and of itself, it can do nothing. So how do we convert chemical energy? What's the only other form of energy chemical energy can turn into? Heat, right? It turns into heat because we set it on fire, okay, and it gets hot, right? Now, that heat within your engine makes gases expand, because we know when things get hot, they expand. So we detonate the fuel, that is, we set it on fire and it blows up. There's small explosions going on inside your car's engine all the time, okay? Those explosions cause expanding gases to push on the pistons that are inside your engine, and the pistons move down. That's what's called the power stroke, okay? That moves the piston down, which drives the drivetrain, which moves your wheels. Everyone follow me there? So we're going from chemical energy to heat to mechanical energy. And if you recall, on the second day of this unit, we talked about how heat is the least useful form of energy. Okay? And that turning heat into mechanical energy is one of the least efficient things you can do. Yet, it is the sole driving force for almost every motor vehicle on the planet. Yeah. Okay? It's unfortunate, but that's how we do it, right? Okay? Now, could you drive an electric car? Sure. How many of us do? Not me, and I don't want to. I'll say it. I don't want to drive an electric car. Okay? I don't want an electric car because I drive a truck, and I don't want an electric truck because it won't do the things a truck's supposed to do. Okay, you know, if I didn't have to worry about that, and I knew that I could get from home to work and back again in an electric car, I would probably do it. Okay, but the reality of it is that electric car technology has come a long way, but there are still some serious limitations. What are the limitations to an electric car? Right. Yeah. You have to sit and charge, and the charging cycle takes several hours. Okay, so you're not going on a road trip in an electric car. Okay, you had best be able to be at your destination if you're driving a very efficient electric car in around 3 hours to 3.5 hours. Okay, beyond that, you will be out of juice, and then you'll have to wait several hours for your batteries to recharge. Okay, so there's some inconvenience factor to that. Gas is easier. You just stick the pump in and you squeeze it, and then you're in 5 minutes you're good to go again. Okay, but in an electric car that doesn't work. Okay, if you're commuting back and forth, then an electric car is an excellent option because you only have to go for about, and if you, let's say you're driving in downtown Calgary, okay, even in terrible traffic, probably the worst that's going to take you is an hour and a half, and then you can have your car plugged in maybe while you're at work, and it can charge up and be ready to go for when we go home. In that case, it's an ideal solution. Right? Which is why they're far more popular in like California and places like that, because that's kind of more like what they do. Okay? Whereas in Alberta, if I want to go all the way to Edmonton and the roads are bad, and it's going to take me more than 3 hours, and I might have to stop in Wetaskiwin and plug in for a couple hours and then go. Okay? The other problem is that electric cars do work better under predictable temperatures. Okay? Under really cold temperatures, batteries are not as reliable. Okay, they don't produce as much power. They don't retain as much power. So if it was minus 30, okay, your range might be affected on something like that. Okay. On the plus side, if you've ever seen any of the performance data from the electric cars, it used to be, I don't want an electric car because they're underpowered and they look dumb and they don't go very fast. Actually, the new Tesla is faster than a 707 horsepower Hellcat Charger or Challenger, okay, which is about as powerful as you can make a production car, and they're more powerful than that. Okay? They're faster than that. Okay? But again, you have a range issue, right? There's things like that. Are they way more efficient than an internal combustion engine? Yes, they are. Okay? A fully electric vehicle is far more efficient. Okay, consider this though. A lot of people go to an electric car for what reason? Why do they go to an electric car, a lot of people? Okay, part of it's economy, but let's think about that. I mean, sometimes gas is expensive, sometimes it's not. Like this weekend, it changed price by 10 cents. Again, it seems to flip-flop by about 10 cents a week lately. Okay, but if it takes 100,000 joules worth of energy to get to work, does it matter whether I'm using 100,000 joules of electricity or 100,000 joules of gas? Does it make any difference? I mean, I need more energy in a less efficient vehicle, certainly. Okay, but is there an advantage? Does it save me energy? It might. If it's more efficient, it might save some energy. Okay, what's another reason? Yeah, a lot of people choose an electric vehicle because they want to reduce their carbon footprint. Okay, they don't want to emit greenhouse gases, and they don't want to, have all the pollution that comes from an internal combustion engine. Okay. If you do that here in Alberta, are you actually reducing your carbon footprint? Where do we get all of our electricity from? Oh, that's not all. That's not fair. Where does 93% of all of our electricity come from? Burning coal. So buying an electric car doesn't reduce your carbon footprint in Alberta. You simply draw more from the electricity grid, which makes us burn more coal, which in the end produces just as much greenhouse gas as driving your car with fuel in it. Okay? Now, if you're in an area where maybe your electricity is produced through nuclear power or more hydroelectric or maybe solar, okay, then yes, choosing an electric car is reducing your carbon footprint. It's too bad Leonardo DiCaprio isn't listening to all this. He could learn something. Did you guys hear about that? His whole Chinook debacle. You should always think before you open your face and say stupid stuff. That's okay. He's probably on his boat somewhere enjoying himself. His boat that runs on solar power and rainbows. Okay. Yeah, so you have to always consider. I mean, if you want to do something good for the environment, just make sure that you really are doing something good for the environment. Going to an electric car in Alberta doesn't really save the environment anything. Okay. What about hybrid cars? How do they work? Anybody know? Right, they're half electric and they're half gas. Okay, so they have an internal combustion engine that's usually a little smaller because it doesn't need to be as big, because they have the electric motors that assist the internal combustion engine. What kind of driving does a hybrid car work best in? Stop and go traffic or on the highway? Stop and go traffic. Okay. Again, a lot of people choose a hybrid vehicle and then they drive it on the highway all the time. And in the end, they're not actually saving themselves very much in terms of money on gas or in terms of environmental impact, because the electric motors only work when the car is under load. And that is when you're trying to accelerate away, you're trying to change your speed, then the electric motors kick in to assist the internal combustion engine, so it doesn't have to work as hard. And again, you can have a smaller motor which uses less fuel. But if you're just driving on the highway all the time, it runs on the internal combustion engine. It doesn't run on the electric motor. Okay, so you always have to kind of understand what you're going to be doing with it and whether it's actually going to do what you think. Okay, otherwise you're going to end up like Leonardo DiCaprio, and you're just going to have this thing and you're going to tell people that it does something. Smart people are going to look at you and go, no, it doesn't. You're just trying to be a yuppie idiot, right? Because you think you're doing something good and you're trying to make this image that you're doing something good, but you don't understand how it works. Okay? So it's important to do that so that when people ask you a question like that, you can go, no, I bought this hybrid vehicle because I know that I'm doing this and it actually is going to save me money. Or I bought this electric vehicle because I have a giant farm of solar panels in my backyard that I use to charge it with, okay? Or something like that. Okay? Otherwise, really all you're doing is plugging it into a campfire. Okay? I mean, that's really in Alberta essentially what you're doing. Does that sort of make sense? Okay. Efficiency. After my little rant, I just thought that was so funny last week. I just laughed so hard. Okay, so useful energy and efficiency. Obviously, any machine has a job to do, and we want it to do that job as efficiently as possible. That is, to use as much of the energy that we put into it to actually do that job and to waste very little. Okay? Reality of it is, any machine with moving parts is not going to be 100% efficient, because there's going to be places where the moving parts touch. And where they touch, there's going to be friction. Okay? And friction is the enemy of efficiency. Okay? Anytime there's friction, there's going to be energy lost to sound, to heat. Okay? There's going to be wear on moving parts, right? Things like that. All right. So we have our initial energy source, which we call the energy input. Okay? We have the useful work output. Okay? That's the energy that the job is trying to do. Okay? And then we've got the efficiency. So essentially it works like this. Okay? Efficiency is going to equal the amount of useful work that's done. Okay? So that's W. Okay? Sorry, useful work output. Okay? And we want to have that useful work that actually gets done. Okay? So the useful work, and we're going to divide that by the amount of energy that we had to put in. Okay? That's going to tell us how efficient the vehicle or machine or whatever it was is. Okay, we take how much take the energy or the work, sorry, not the energy, the work that it does, and divide it by how much energy we had to put in. Okay, that's going to give us our number. Okay, your car right here. This is a chart of all the places energy goes in your car. All right. The exhaust system. What is the exhaust system on your car? What is it? It's a tube. Okay? It is a pipe. A pipe that vents the gases produced in combustion, that would be carbon dioxide, carbon monoxide, and all the other things that are produced when you burn fuel, and it vents it out behind the vehicle so that it doesn't enter the passenger cabin where it could kill you. Okay? That is essentially the sole purpose of the exhaust system. It, however, uses 33% of the energy in your fuel because the gases are hot, and heat doesn't do anything, okay, once it's out of the combustion chamber. Yes, we wanted the heat to expand the gases to move the piston, but once that's, a lot of that heat doesn't actually do that. A lot of that heat just bleeds away, okay, and it goes out through the exhaust valves of the cylinder, and it goes out through the back of the car, and we see that obviously on a cold day, and you can see the steam coming out of the back of the tailpipe. Okay, if it's a really cold day, it looks like sometimes water is coming out of the back of the tailpipe. Okay, why does water come out of there? Right, and actually on a really cold day, it gets cold enough that some of the steam that normally just comes out that we don't even notice actually condenses inside the exhaust system, and the force of the air moving through can actually push some of the water out. Okay, all right, so does your exhaust system push your car forward? Okay, so that's useless. Okay, there's a 1/3 of the energy, there's 1/3 of your tank of gas, and you haven't moved forward yet. Okay, that's just gases going out the back of your car. Okay, cooling and heating system. Your car is so inefficient, it has to have a system to keep it from melting down. That would be the water pump, okay, and the coolant and the radiator. Okay, so you have a water pump in there that pumps coolant throughout the engine block. That's the kind of big solid part of your engine that houses the pistons and the crankshaft and all that kind of stuff. Okay, so coolant gets circulated through there. The coolant's that green stuff. If it's ever leaking out of your car, you should get it fixed. It's kind of important. Okay, it's also toxic to animals, but it's very sweet. So it's actually quite dangerous if you have pets. So if you ever see a green puddle underneath your vehicle, keep your pets away from it. Okay? Because ethylene glycol is very, very sweet, but it's also very, very toxic. So anyway, you don't want that to leak out. What it does is it circulates through, and obviously the second law of thermodynamics allows heat from your engine to be absorbed by the coolant, which then gets circulated to your radiator. Radiator's on the very front of the engine compartment. If you actually look kind of through the grill of your car at the front, you can see it. It looks like these little tiny metal fins, a whole bunch of them, and kind of a big square. Okay, so cool air from the outside goes through the radiator and cools the coolant, which then gets circulated back by the water pump through the engine. Okay, water pump's a pump. It's attached to your engine block by either a belt or a chain. Okay, and that system uses 33% of the energy in your fuel. Does it move your car forward? Okay, we've used 2/3 of a tank of gas. We have not gone anywhere yet. Okay, we still are just keeping the car running. Okay, keeping ourselves alive by venting toxic gas and keeping the engine from melting down. Yeah, they're important jobs. Okay, but they don't drive the car forward. Okay, drivetrain. Okay, drivetrain would include crankshaft. If you have an all-wheel drive system, that number would be bigger. Four-wheel drive system, that number will be bigger. Transmission, okay, things like that. Are those an important part of allowing your car to produce power? Yes. Okay. There's a lot of friction, though, because that's where a lot of moving parts are. Agreed? Okay. Still doesn't move your car forward. Okay, it's part of it, but it's not actually actively moving the car forward. Okay, your accessories. What are accessories? Yeah, your radio, your power windows, power door locks, air conditioner, okay, things like that. Those are your accessories. Rear window defroster if you got one of those. Okay, defogging mirrors if you have those. Okay, kind of the fancy stuff. If you got the heated seats, that's an accessory. Okay, that kind of stuff. All right, those are all nice to have, but do they move your car forward? No. Okay, if you are the guy that I can hear 2 blocks from my house when he's driving, that guy's, I can hear him a mile away. Okay, this number is higher than. Okay, because I knew a kid back when I was in Lloydminster. Every year we had this car show. The kids they would bring in their cars and we'd have a car show with the kids' cars, and he had to have 2 alternators the one that was actually on the car, an alternator, sorry, is attached to the crank by either a belt or a chain and generates electricity. Okay, it charges your battery up and it runs all the electrical things, accessories in your car. If you have a really big stereo, you need two of those. He had to have an extra one put on to power his stereo. Okay, and then he had his stereo. He did what was called the loony dance. He would put a loony on the top of the car. The paint job was a mess. The stereo was worth 5 times the car was worth. He put a loony on the top of the car, and then he cranked the stereo. And the loony would bounce all over the top of the car from his stereo. Okay? This number was probably more like 8 or 10% for him. Okay? On a normal vehicle, it's about 4%. Still not moving the car forward. Okay, internal friction. Obviously, that doesn't move the car forward, does it? Okay? It's another 6%. Useful energy that's left that propels the car forward, 14%. So you spend $100 to get $14 worth of movement out of your car. Okay? Almost, it's a bit of a travesty, but we accept it each and every day. Okay? Now, are cars more efficient now? Yes, most certainly they are. Okay? Cars are way more efficient than they were even 5 years ago. Okay? And back in my day, you know, if you had a car that got 30 miles per gallon, man, you were probably driving like a little tiny two-door Honda Civic hatchback. Okay? Now you can get that from some trucks, okay, where they were getting that much better at making things efficient. But certainly, it's still a kind of a low number, right? In Alberta, how many people carpool? Yeah, you? Okay. How many of you came to school in a car that had more than 2 people in it? Okay. Now, I asked that of a grade 11 class where everyone has their driver's license. 2 hands will go up. Yes, a bus count. Yeah, that's what I'm saying. If I asked this of a grade 11 class, once people have got their license in a car, practically no hands will go up anymore. Okay? When you guys get your license, drive down the Deerfoot, pay attention to what you're doing. Okay? But if you look around as people pass you, I will bet you that 8 out of every 10 cars has only 1 person in it. Okay? We're not mindful of things like that all the time. Okay? Very few people carpool. Right? Very few people take public transit in Alberta. Okay? A few more obviously in the city, but you can't take public transit in Okotoks because we don't have any. Right? In rural Alberta, places like here, we just don't have that ability. Okay? It costs a lot of money to have public transit. So we're not very efficient. We use a lot of energy. Okay? But on the same side of that, there's obviously Alberta is not a very big population place either. Okay? So we're still pretty good for carbon footprint. Okay. So systems with moving parts are always going to lose energy. Okay? They're going to lose energy because of friction. They're going to lose it as heat. Okay? And we already said our engines need to lose so much heat that they have to have a system that takes 1/3 of their energy just to keep them from melting down. Okay? So that's consistent with the first and second laws of thermodynamics. We're always going to have energy going away before it does useful work. Okay? Energy supplied to your body by food energy has to equal the energy of all the useful work done plus all the wasted energy, which includes heat and the mechanical energy of the parts of your body. Okay? Is the human body pretty efficient? It's okay. Do you still put off a lot of heat? Yeah. Okay? I mean, that's how the police find crooks at night, right? They put on the FLIR camera, forward-looking infrared, okay, and you stick out like a sore thumb. Okay, if you're just, if you're a police officer, you're looking for someone in the bush, you have no hope of finding them just with your eyes because it's too dark. Okay, but they fly over top with the helicopter with the infrared camera, and they know exactly where you are. Okay, because your body doesn't work all that efficiently. You're 37 degrees Celsius. Okay, if it's minus 30 outside, okay, you glow like a second sun in infrared. Okay, because we're putting off all this kind of wasted energy. Okay, so according to the second law, obviously heat flows from hot to cold, okay, and it can be made to do work if anything is put there in between. That's the idea of the heat engine that we talked about before. Okay, however, during the thermal energy transfer, some energy is always lost to the surroundings, okay? So the efficiency of a system can never be 100%. Okay? That means you can never come close to getting all the energy out of a system you put into it. Now, we were saying internal combustion engines aren't very efficient. Are electric motors efficient? Actually, electric motors are quite efficient. Okay? Why is an electric motor so much more efficient than an internal combustion engine? Yeah, there's no conversion of heat to mechanical energy. It's electrical energy directly to mechanical energy. Okay? So there's less conversions along the way. The less conversions you have, the less places where energy is lost. Because every time you convert one form to another, energy is going to be lost because no conversion is 100% efficient. So the more times you convert, the more energy you're going to lose. Well, electrical energy converts directly to mechanical in an electrical motor. Okay? So you only have one energy conversion. How much friction is there in an electric motor? You guys did this in grade 9, right? You did electricity in grade 9? Okay. Did you build an electric motor with the magnets? Some of you did, some of you didn't. Okay. In an electric motor, you've got essentially, in a simple one, 2 magnets, but in a big one, you have many magnets kind of arranged in a circle. All right. And what happens is you reverse the polarity of the magnets because they're electromagnets. You make them north-south, and essentially it repels the driving part, the drive shaft in the middle. Okay. So if you try and put 2 magnets that are the same pole together, what do? Can you put them together? No. So is there as much friction in an electric motor? Not nearly as much. Okay? So they're more efficient in that way because they have less metal-on-metal contact. Right? An electric motor can run well over 90% efficiency. Okay? What kills an electric motor is whatever it's attached to. Okay? Yes, the electric motor, if you didn't attach it to anything, would just whir along happily and be pretty efficient. Okay? Problem is, whatever you attach it to, that's going to have drag and things like that. For example, a fan. Okay? A fan is really just an electric motor, but then you've got the fan blade on there. Well, as soon as the fan blade gets moving, is there a lot of resistance? Yeah, that's how what it's designed to do is move air that's stationary, and it does that by exerting a force on it. Okay? So that resists, and then that's where kind of, but the motor itself is actually quite efficient. All right, so efficiency is a measurement of how effectively a machine converts energy into useful energy output. So it converts energy input into useful energy output. And it's expressed simply as a ratio. Okay? Useful work output divided by the total work we put in, or the total energy that we put in. So EM divided by EI, okay, gives us our efficiency. I'm going to take this part about multiply by 100 out, just because it makes the formula easier to manipulate. Okay? When you guys calculate your percentage on a test, do you bother multiplying by 100 after, or can you just convert the decimal? Yeah, you can convert the decimal in your head, right? If it comes out to 0.85, you got 85%, right? So we don't need to have this times 100 part in here. Okay? We're just going to say useful work divided by total work equals percent efficiency. Okay? Is that a pretty easy one to manipulate then? Yeah. All right. So some machines involve the conversion of mechanical energy into another form of mechanical energy. Okay, so for example, a crane uses mechanical energy to do the work of lifting a load vertically to the top of the building, and the load gains mechanical energy. Okay, but it's converting either, it's probably using fuel, or maybe it's a big electric motor, whichever. Okay, but it's still converting from the movement of the motor to the potential energy of the load. Okay, it's doing that through the tension in the cable. Okay, so types of engines. Automotive internal combustion engine, 12 to 15. I'd say now that number is more like 14 to 20. Okay, engines are more efficient. Electric engine up to 95%. Okay, steam reciprocal engines, 50 to 75. Okay, we don't. That would be kind of like a. I'm trying to think of something that would use that, and I'm drawing a total blank. Okay, steam turbine engine. Okay, turbines would be like what we use to generate electricity after we burn the coal. We use the coal to get heat, which then turns water into steam, and the steam turns a turbine. All right, so is the way we generate electricity very efficient? Okay, if you've ever driven on Stony Trail toward Cross Iron Mills, right there at the north end of Calgary, and you turn that corner, you see that power plant there, right? It's always got steam coming out the top, right? Okay, coal-fired electricity plant. Okay, and it's just pumping. All that steam is all the wasted heat, okay, that came from making steam to turn the turbines. Okay, so there's a lot of energy that gets used up there. Okay, electric engines. What other kinds of things run on electrical engines besides cars? And they're big. Really, really big. Some of them are several hundred meters long. Nope. Trains are usually diesel, unless, at least in Canada, but yeah, in Europe and Japan and places like that, they do have the electric monorail type trains, yeah. Okay, wasn't the one I was thinking of, though. Nope, airplane runs on internal, well, it's not internal combustion, it's a combustion turbine. Boats, specifically naval vessels, okay, modern aircraft carriers, submarines. They run on nuclear power. The nuclear power generates electricity that turns their motors, okay? A modern aircraft carrier runs on an electrical engine, or several of them, okay? A nuclear submarine is electrical. Okay, makes them quiet, makes them efficient, and for a submarine, you don't have to worry about where you get the oxygen to burn the fuel from. Okay? That was the big problem with early submarines. Okay, they could go underwater for about an hour and a half before the batteries ran out, and they had to come up and run the engines to charge the batteries again. Okay, they were essentially like the first hybrid vehicles. Okay, they had a diesel engine and they had an electrical engine. Right, but now with nuclear power, you can send a sub or a ship out, and they don't have to come back for 20 years to refuel. They got to come back and get food. Okay? They don't have to refuel. Right? Is it pretty efficient to use electricity? Sure it is. What's the drawback of nuclear power? Not so much how much, just they're really bad. Okay? I mean, like a nuclear-powered submarine, in its useful lifetime, will probably produce, let's say, maybe 2 barrels. 2 like, kind of oil drum size things worth of nuclear waste. The problem is, what do you do with that? Right? If you have an internal combustion engine, the carbon dioxide goes in the atmosphere, and we hope the plants take care of it. And usually they do. You can't dump nuclear waste on plants. They're not going to like that, and they're not going to take care of that for you. Okay? You have to dig a deep hole and bury it in the ground and never, ever go back. Right? The process of disposing of nuclear waste is very, very intensive. Okay, there's very few places in the world where they actually have the facilities for that. Right, you basically have to have the right kind of bedrock, the right kind of clay and things like that. You dig a big deep hole, you put the barrels in there, you fill the hole with concrete, and you cover it up and put a sign around it that says, "Don't dig a hole here." Okay, yeah, right. So it can be pretty nasty stuff. And how long is it toxic for? A long time. Hundreds to thousands of years, depending on what type of nuclear waste you have. Okay, let's look at this first example here. Got a crane that lifts a load of construction materials from the ground to the second floor of a building. In the process, it does 2.3 times 10 to the 4 joules of work, okay? While doing only 8.0 times 10 to the 3 joules of useful work. Okay, so it's using this much energy, but only doing this much useful work. How would you be able to tell the difference in a question? Because, I mean, it said work and then it said useful work. How am I going to know which number is going to go on top, even if I'm having trouble with the wording? Smaller one's always going on top, right? Okay, if you do one of these questions and you get a number greater than 1, you flip the numbers. Okay? Because if you get a number greater than 1, you're running at more than 100% efficiency, which means your machine is making energy from nowhere. It's breaking the first law of thermodynamics. Okay? So you know that you did something wrong. You flip the 2 numbers. Okay? The smaller number is always going to be the one that goes on the top. All right, so we're looking for what the percent efficiency is. Okay, so the mechanical or useful work output is 8,000 joules. That's what 8.3 times, or 8.0 times 10 to the 3 was. We talked about that last week, right? The scientific notation. Okay, and the energy input, okay, the energy I had to put in was 24,000 joules. All right, so the efficiency is going to be 8,000 divided by 24,000. Right, and that should come out to 30.348, right? Right, so this thing's running at 34.8% efficiency. Making sense? All right, what if I had to solve instead for, let's say maybe it gave me the efficiency and gave me the useful work, or sorry, the work input and wanted me to calculate the useful work, then what would I do? Multiply them, right? It's just a 3-variable formula. Okay. Okay. We're going to have you do, I've got a sheet here that's got 8 efficiency problems on it. Probably take us 15 minutes or so. Okay. They're pretty easy. Okay. And then after that, we're going to talk a little bit more about law of conservation of energy. Okay. Tomorrow you're going to be doing a lab on conversion of energy. Okay, trick to the last one. I need to calculate how much useful work is done in lifting this thing up. Agreed? Would that be the change in its potential energy from ground level? Yes, it would. All right, I know its mass, and I know how high it's going to be lifted. So I can calculate its potential energy. Well, I don't need the I there. Okay, its potential energy at the end here, right? By going 2,000 times 9.81 times 5, right? That'll give me the number that goes on the top of the efficiency equation. Okay, that'll be my useful work output. Okay, so EM. Okay, and then we're looking for EI in this case. How much work do I actually have to put in to do this much work? Right, I think, what does this come out to? 498,100? Is that right? That's too many zeros. 98,100. Okay, so I've got the efficiency, 35%. I've got the useful work that's going to be done. I need to calculate EI. So I'm just going to switch EI and efficiency. So I'm going to have EI equals 98,100 divided by 0.35, okay, the efficiency. And when I do that, I should get my 280,285.71 joules. Okay. I told you what was on the test last week. Did I tell you there'd be any efficiency problems in the written response? Good, because there aren't any. Okay. Is this a relatively simple equation to use? Where are you going to find it? Yep. 1. Okay. The idea here is that we talk about efficiency, we go over some examples, we go over some applications. It's just a percentage. Okay. As long as you understand, I'm more concerned that you understand what efficiency is and its applications than I am of whether you can, move around a 3-variable formula. Okay. I know you can do that. So everybody with me there? Okay. Now, okay, so let's have last look here at a law of conservation of energy question. Okay, I want you to calculate the speed of this car as it goes down this hill. Okay, it starts 45 meters above the bottom, moving at 8 meters per second. At the end of our question, it's still 6 meters from the bottom, and I want to know how fast it's going at that point. No, you know what? It's at the bottom. I know it doesn't look like that, but it is. It's at the bottom. Okay, I want to know how fast it's going at the bottom. All right, so obviously there's no work being done anywhere along the way, so it's a law of conservation of energy question. Okay, initially it has both kinds of energy. It's got some potential and it's got some kinetic. Okay, but at the end it only has kinetic because it's at the bottom of the hill. All right, so we've got, can we eliminate M? Good, because we didn't get it anyway. All right, so I'm just going to go straight to that. GHI plus 1/2 VI squared equals 1/2 of VF squared. Okay, and this is what I'm looking for. So to manipulate, what do I do at the half? Right, and then what? Square root it. Okay, so when we plug in our numbers here, it's going to be 9.81 times 45 plus 1/2 times 8 squared divided by 1/2. Okay, and when we plug that in, we should get 30.77 meters per second. Okay, where'd I lose you? Okay. All right, so tomorrow we're going to be doing a lab, okay, where we'll have the rubber bands out again, and we'll be shooting the cars, okay, and measuring how far they go and figuring out how much of our work in pulling back the rubber band is going to get turned into actual mechanical energy for the cart, and just how ridiculously inefficient that conversion actually is. Okay, because it is terribly inefficient. Now, should you, when doing that lab, arrive at a number that says your efficiency is greater than 100, we've got to figure out what you did and repeat it so we can all get rich.